Sir,
Yes.
hi. If I may, when you posted the notes from the second class
Mhm.
for the recording that didn't work, it was actually the notes from the first class. So we never got the notes from the second class.
Oh, are you sure?
Yeah,
Oh, sorry about that.
it's okay.
You
So
can email me and I'll.
yeah, I'll do that. It's just yeah.
Okay, anyways, I'll check it after. All right. Oh, yeah, you're right. Okay. Okay, just changed it. All right. So welcome everybody. Yeah, so let's start. Okay, so if you have looked at Moodle, you may have realized that yeah, a few things have been added. First of all, yeah, you're going to have a separate Zoom link for the TA sessions, which are just after the class. I apologize in advance for the way things are in terms of the schedule. I've just asked the dean if it's possible to change something, and he says no. Well, I don't know what you think, but I think 1 hour of math is enough in one day. So 3 hours is quite a lot. And then if you have the 3 hour class plus 1 hour of TA session, it's just overwhelming. But that's the way they made things. I don't know. Would would somebody be completely opposed to changing? I'm not saying it's possible, but like if we could spread this class around more during the week to make it more palatable. would that really mess up somebody's schedule? I guess the question would be what time would we replace it? But yeah. Okay, anyways, I shouldn't ask that question because I asked the dean and he said it's impossible. But yeah, next year it's going to be different because I apologize for the fact that yeah, you have 4 hours of math following all following each other on Fridays. Okay, so that's one thing. So you're going to meet your new TA, which who is very nice. Her name is Sati, and you can do the exercises for the first part of the class that we've seen. Other thing I've posted is the homework. So it's not too difficult. I think it's feasible, and you have 2 weeks to do it. So and you can do it. I think I wrote in teams of 3 or 2 or 3. Let me check. Yeah, up to 3 people. So 1, 2, or 3 people. And yeah, so do your best, and yeah, it shouldn't be too difficult, in my opinion. Oh, by the way, somebody was scared. Oh, do you have some test today? So that was my first idea of how the class would work. But before we started, I updated the class outline. So instead of tests, you have these homework assignments. So don't worry, you don't have a test right now. But yeah, are there any questions about this? About the homework?
I have a quick question about the tutorials. Will they be recorded and uploaded?
Yeah, so I've made it automatic that they be recorded. A problem I'm having right now is for some reason that the TA cannot access the Moodle page, so it's harder for her to post the videos. But yeah, we'll try to fix this.
Thank you.
Okay, so last time, if you remember, by the way, sorry about the video. So what happened is it was disconnected just after the first half, and I thought, oh, should I stop the class and start over again? But it looked like everything was still working, so I thought, okay, let's hope. But no, after that, Zoom wasn't able to create the video. So we have only a half, but yeah, it's not too deep material yet. Yeah, so why don't we start by some quiz? By the way, I forgot to give you one of the quizzes of last week, but still we can have one quiz today. So it's a quiz about partial equilibria. So it's just to see if you remember what you did last week. So of course it doesn't count. It's just you do your best. Where's my window? Right. So how about this thing? So I posted it in the discussion. Yeah, so up to now, it should be stuff that's doable for you because you've done some economics before. So please, someone tell me if there's something wrong with the quiz. Right, how many answers do we have? 17. So let's say 20 seconds more. If you don't know, just answer at random. Yeah, so most of you got it right. Let me just share briefly. Okay. Question 1. Consider the inverse demand function PD of Q equals 8 minus 2Q inverse supply PS of Q equals 2Q. So yeah, sorry for starting the day with a test, but yeah, that's where we were. Anyways, that's good to make your mind work a bit. What is the equilibrium? Well, I guess most of you computed 8 minus 2Q equals 2Q and got 2 as the right answer. So yeah, no, I'm sure this 4 there is just a slip of the mouse. Now consider the demand function QD equals A minus BP. So that's exactly the same thing. It's just that now if we do it with letters, then we don't have to do it again for the rest of our lives because we already know by heart what it's going to give us. So A minus BP and CP. Yeah, so the right answer is that equilibrium price is A divided by B plus C. All right, and now last question. If the parameter A increases, how would the equilibrium quantity change? So, well, of course, now we have price. So how do we find the equilibrium quantity? Well, we can substitute A divided by B plus C in here, for instance. And we're going to find that it is equal to, I think it's AC divided by B plus C. And then the question is, if the parameter A increases, how would the equilibrium quantity change? And it's not necessarily obvious if no, actually, yeah, no, it is obvious. It is obvious. It is positive. Yeah, sorry. So what do we do here when we are asking these things? It's called comparative statics. So we have some parameters, then we compute the equilibrium, and then we ask ourselves, oh, if some parameter changes in some way, what happens to the equilibrium? And this is redoing economics. This is asking yourself, oh, I don't know how the world works, but let me design a model that fits my idea with some parameters that can change, and then ask myself, so what would happen? So for instance, A here is A represents in some way the maximum amount of money that the first buyer is going to no, sorry, the maximum quantity that that would be bought at most if the price was 0. So then if it increases, then of course it's going to increase quantity, so it makes sense. So maybe I should have asked something about B or C. It would be more interesting. Anyways, question about the quiz? No? All right. So let's continue the class. Yeah, so this was my computation. Okay, so last time we had seen solving a system of 2 linear equations. And as I can see, you guys are pretty good at it. So let's have some more applications. So So now let's do some economics. So simplest Keynesian national income model. So this is something you might see in macro, or although it's super simple. So here, this is output, which is divided into 3 quantities: consumption, investment, and government expenditure. And here, what Keynes is saying is that since I put a 0 here, it means it's something that never changes. It's some parameter of my model. But the only thing that is not a parameter is what doesn't have a 0. So it's Y and C, so output and consumption. And consumption equals to a positive function of output. So the higher the output, then the more consumption I have. Oops. And what I assume is, that investment is fixed. So whatever my output is, I always invest the same amount of resources, and government expenditure is fixed. All right, so where Y is national income, C is consumption, I0 is investment, and G0 is government spending. And assumption, A is a parameter that's larger than 0, and B is between 0 and 1. So questions. Which are the variables here? If you think it's easy, then you're right. It's not. There's no. There's no trick. Nobody knows what are the variables in this model as opposed to parameter.
Would they be Y and C?
Yes. Y and C. Because A is parameter, B is parameter, and here we see that investment is constant and government is constant. So that's what we care about finding. Okay, so 2. Let's find the equilibrium values. So I give you a few seconds to do it. Or let's start with Y star. Okay, so I see that there's a proposal here. Okay, yeah, so show the chat. Because in my other class, I have like 300 people, so the chat is just all over the place, but I see that here it's useful. All right, so I'm very happy that somebody answered C minus A divided by B, because this is something super important. So I will try to remember to write it every time in the exam, but if I forget, still do it. So as function of the parameters. Because here we said that y is a variable and c is a variable. So if you say that y equals to, so here what for instance, if we say that c equals to a plus by, so then what I could just say is, here I have minus a and I divide by b. So it's not false, but is it better? Well, not really, because I don't know what C is. So if we had already asked previously what is C star, and we had an answer, then fine. But then if you say, oh yes, C star is A plus by star, and y star is C star minus A over B, then okay, what is so it's circular, so I'm not any better. I could have just written, oh, I know what y star is, y star equals y star. It's not false. Oh, I see something, new proposal. Yeah, so right, that's the right answer. So yeah, so every time I ask you find the equilibrium values, of course, I want as function of the parameters, as function of what is exogenous. So here, yeah, Mr. Moisin found the right answer. So how should I do it? Well, what I have here is C equals A plus by, so I can just substitute it here. And then I get minus by here. So this is divided by 1 minus b, which comes from here, right? This is y times 1 minus b. So then I can divide it on both sides. I get this. So, yeah. So I put a star to say it's a equilibrium output. All right. So this is super important. And then what is C star? So equilibrium consumption. So yeah, you can do it. So I can tell you. So in that case, I can accept two answers. So I can just say, okay, then I have y star as function of the parameters. So then I'm allowed to say this is equal to y star. So this is being a bit lazy, But then what I can do is substitute it. So, and what is the, so why would it be nice to substitute it? Well, later on, I may ask you stuff like, oh, what's the impact of, say, A or B or G0 on C star? And then, of course, if you have it implicitly, it's not that easy to answer. But here, if I think if I compute it, I can get something like, this gives me, I have A minus B there. So I'm going to get minus AB plus I0 plus G0. Is that it? Am I missing something? I'm not sure. Let's do it properly. Okay, so this is BA, BI0, BG0. This is this, so I can do plus. So A minus AB plus AB. So this goes away. Okay, yeah, I was not close to the solution. And then it's easy for you to say, oh, what happens if A increases, for instance? Then you know for sure that C star is going to increase. So having it explicitly like this is good for comparative statics. So note. Okay, so two things to note. Always, I'm just write it and then you can see. So that's why I ask you what are the variables, because then you cannot use one or the other if you haven't writing them explicitly. Allows to answer questions of comparative statics. Yes, Patrick Adams.
Yeah, just so like in our equation for C, we have the parameter B both in the numerator and the denominator. So like, I guess if you were to ask what's the
impact of B?
relationship between C and B, you'd have to like find the derivative and do it that way.
Exactly. So, and so I guess you maybe are there, but some other students may not be there yet. So we're not talking about derivative yet. But yeah, you're right. That's what we would have to do. So finding, for instance, the impact of B on C star, we would compute the C star dB later. Yeah, I'm going to save this. So what date is it today? It's the 24th. All right. So is that, oh yeah. Okay, now next topic. Solving. So are there questions about this? So here what we have is our linear equations. Now we're going to see higher order stuff. Okay, so solving quadratic equations. So I'm guessing most of you will have seen this before, but yeah, just in case. I'm struggling with my Zoom window. I never know where to put it. Okay, all right. So if we have, of course, now we're back to one single variable. So if we have the equation ax squared plus bx plus c equals 0. What is the solution? For x? Somebody knows?
I'm pretty sure it's b plus or minus the square root of b squared minus 4ac and all of that divided by 2a.
Yeah, exactly. So it's x is equal to then the question is, where does that come from? So
Sure,
everybody is as
so there's a condition, right? B squared minus 4ac has to be greater
oh
than
yeah,
0.
as long as a is not 0. Is that it?
B squared minus 4ac has to be greater than 0.
Not necessarily. I would get complex numbers, but it's fine. I mean, if it's not fine for economics, but yeah, it's something that exists. But point taken. So different solutions. Yeah. First of all, condition A has to be yeah. Yeah, what's my isn't 0, and then types of solution. This b squared minus 4a squared is bigger than 0. I get 2 real roots. B squared minus a squared equals 0. Then I get 1 root. Yeah, 1 real root. Or you could say 2 repeated roots. And then smaller than 0, I get no real roots, but 2 imaginary roots. And we won't care about this in economics, but For the most part, I would say. If we describe dynamic systems, maybe we get this, but it's for much later. All right, so where does that come from? Somebody knows? How do I show that this, for this, the solution will be this?
Sorry, sir. Maybe it's just me. I don't recall what that is. What do you mean by types of solution?
Oh, so I'm looking for solutions for X. So what X values will make this equation true? And these solutions, these values are what we call roots of the polynomial. And yeah, so depending on the values of A, B, and C, then so these are the values that I'm going to get. So I get two, since it's quadratic, I get two possible values. So why is that the case? If it's a quadratic, you know what a parabola is? So it's something like this, for instance. So this it looks quadratic because of the square here. So if there's a parabola that intercepts the horizontal axis in two places, then I know that I have two solutions. But if it doesn't intercept the y-axis, the x-axis, then I know that probably I don't have any solutions. But in the reals, but I may have two imaginary roots.
Right. Yeah, thank you. I got it. Yeah.
All right. So, but anyways, we're going to draw one. So it's so now I'm just going to show you where that comes from. So. So what we're going to try to do is to complete the square. So completing the square is making sure that what we have is a perfect square. And once we have it, then we can just take the square root. So it's going to be much easier. So we know that a squared, if I have a plus b, for instance, then I get a squared plus 2ab plus b squared, right? So that's what we're going to try to do here. So yeah. So I don't want to leave this there because obviously it's not exactly the same as this, but just to show you where we're going. So let's first divide by A everywhere. So this is still true because 0 divided by A is 0. And then if, imagine I have a perfect squared. So this is x squared, and this is the 2 times the product of both variable. And then I would need then my C here. Yeah, let me leave it there. I had A plus B, or let me take 2 other letters. Alpha plus beta squared equals alpha squared plus 2 alpha beta plus beta squared. Okay. Now imagine that this is alpha squared. And now imagine that this is 2 alpha beta. So what would I get as last term here, beta squared? Somebody has an idea?
No.
No. All right. So this is this is alpha multiplied by beta and 2 times. So here I have, this is like alpha squared. So this would be alpha. So I would have beta squared here, such that this is twice alpha times beta. So it would be, so here, so it would be this. So almost, but this this would have to be twice. So I just divided by 2. And then I can, since I'm adding this, I'm going to subtract it 2. All right. And if you check, then I get a perfect square. This is equal to, yeah, if I do the same here, this, if this is x plus, and this is, oh, and this is squared, of course. X plus b over 2a squared, I get x squared plus 2 plus this squared, right? So this is what I want to do. I want to make a perfect square appear. And this here, of course, the 2 is disappearing. So this is, oh yeah, and there's an x here, of course. So this is what I want to make appear. So I have it here. If you're not following everything, I'm messing with your brain. I'm showing you stuff because it's a math class, but yeah, it's going to be easier in exams when I ask you to show stuff. But yeah, you don't have to like learn all these steps by heart. I'm just showing you where they come from. So here I have a perfect square, which is equal to what? X plus b over 2a squared. And here I can put this on the other side. So it's equal to this minus c over a. So what I can take now is the square root of on both sides, because this is a square. So I take the square root. So I get this, and I get square root, and here I have plus or minus. Yeah, and here I can just so here I'm just going to complete my computation. Okay, so I have b squared over 4a squared. So here I'm going to multiply by a and get a squared, and multiply by 4. So I get minus 4ac. And here I have 4ac inside the root. So what I can do is take it out. How do I do that? So this is like if I had root of this divided by root of 4ac. And root of 4ac is 2a. Here, this comes here. And I can yeah, divide by 2a on both sides. Yeah, and still, since I have plus or minus here, I can put this here. All right, so this is how we get it. So I hope it was fun for the people who were interested in where this formula comes from. For the others, yeah, it might be brutal in the morning to see this. But it's fun to see how these things are discovered, because you use it all the time and you don't know where it comes from. So it comes from there. And now, are there... Yeah, so first of all, questions about what we just did? I didn't understand. Is there some step I did that you didn't understand? We dropped an X for no reason. Yeah, okay, so here it was. So x squared plus b over 8 times x plus b over 2a squared. So here it is. So this is equal to x plus b over 2a squared. Why? Because I get this x squared plus this b over 2a squared plus the double product of both. So x times b over 2a. And then times 2. So this is where this x went. It's just that we found this thing instead. Yes, that's exactly it. Yeah, it's b over 2a as one of the variables, quote unquote. So are there formulas like this for higher order equations, like with x3, for instance, or x4? Do you know?
I believe there's one for x3, but I forgot.
Yeah, so this was a big research and development. Yes, yes, very good. Who said that? Does this break down after x4? Yeah, Mr. Jacobi, you're absolutely right. So this was, yeah, top secret research back in the Middle Ages in Italy, for instance. People were after a formula that would allow them to solve cubic equation and quartic equations. So there's the first real cubic formula was published by Girolamo Cardano, and Lodovico Ferrari published it in for quartic in 1545. But it's absolutely true that after quartic, there's a theorem. It's a Abel-Ruffini theorem that shows that there cannot be a formula like this for higher powers. It has to do with Galois. Yeah, it's so I'm not getting into that, but yeah, it's amazing that we can show that there can be no equations with just roots and exponents and fractions and addition and subtraction for higher order than 4. But don't worry, we're not going to go higher orders than this. Okay. So yeah, let's have a little example. a quadratic domain. So we only had linear stuff for now, but let's have a quadratic stuff. 10 minus p squared and s equals 3p. Then if I want to find the equilibrium, so again, I take QD equals to QS. Oops. And I find 10 minus p squared equals to 3p squared. 3p. Oh yeah, sorry, my example was with 3p. I don't know if 3p squared works, but probably. So then what should I do? Well, I am going to do as I did before. So I'm going to make sure that the p squared has a positive sign. So then I can express everything easily. So I get p squared. This is plus 3p minus 10 equals 0. P would be equal to what? Can somebody tell me? No, you're sleeping maybe. So I use the quadratic formula. Oh, good. Perfect. Thank you. Yeah, so exactly. Oh, no, I think I got something different. So let's see who's right. All right, so minus b is minus 3. Plus or minus root of 9 minus 4 times 1 times minus 10 divided by 2 times 1. Yeah, I think that's minus 5 and 2. So I get, yeah, so this is something that that you're going to find is I really hate not having good numbers. So in your exam, it's possible if you find some number that looks strange that it's the right answer, but most probably not, because yeah, so that's plus 40. So 9 plus 40 is 49. So that's equal to plus or minus 7. So that's, this is divided by 2. So it's 10 divided by 2. So, sorry, it's minus 3. Plus 7 is 4. Divided by 2, that's 2. Or, yeah, minus 5. And then are we happy with both, or do we keep one and drop the other?
Do we keep negative values?
Yeah,
Don't think we do, right?
no, because we never pay with negative prices. No. So what we're going to say is, so only solution. Yeah, you could write it this way. That's fine, but it's, yeah, so it's the right answer. So Mr. Deng asks, could we write p minus 2 times p plus 5? Yes, the solution is there too. So, but if I'm asking you, please give me explicitly what is going to be the equilibrium price and equilibrium quantity, then so I keep p star equals 2 and q star equals to 6. Yeah, equals 3p star plus 6. All right, so now I can ask you, please draw this system. If we're talking about subsidies, yeah, in a way, yes, it would be a specific context. But thing is, if you get two values, one being negative because I'm giving you some quadratic function, then yeah, probably I just care about the positive one. But it's true that in a way, a negative tax is a subsidy and a negative subsidy is a positive tax. So you could get negative solution if you were looking for a tax and in the end, the right answer is a subsidy. I don't know. I don't want to say, I don't have a specific example in mind, but who knows? Everything is possible. If it's a price, then yeah, stick with the positive value. So if I have a quadratic system, how should I draw it? Yes, find 3 points. So with linear equations, 2 points is fine with quadratics. We need at least 3 points. So we have one. We have let's say we have Q. So for, of course, what we want to draw here is this. So for Q equals, so we have Q D P equals 6 and 2. That's one. Do we have other points that we could use? Yeah, let's try that. So let's first let's see p equals 0. I get q equals to 10, right? If I substitute with a 0, and now q equals 0, I get square root of 10. So that's not too fun. Is there a better one? 9-1, yeah, 9-1 would be good. So here I can just show what happens if I have 1. So I get that p squared equals to 10 minus 1 equal 9. So I'm going to get that p equals 3. Yeah, so 3 I think was the suggestion, maybe. So 1 q equals to 1 is equals to oh, am I confused now? What did I do? So q equals 1, then p equals 3. Yeah, it makes sense. All right. Uh, 9-1, are you sure about this? Or is it the reverse? Okay, I get this. This too. Um, 10 minus 1. Oh, yeah. Equals 9. Yeah, so I can. So I have a fourth one. Nine and 1. Okay, I have a lot. Well, actually, now that I think about it, I prefer putting the p on the vertical axis. So let me just reverse everything. Sorry if you've been writing. And 3-1. Yeah, it's just for our friend Marshall. Okay. All right. And I think one of the questions in the homework is to do this kind of thing. So yeah, pay attention. So we have Q here and P here. So yeah, what points did I have? Uh, 2, 6. So that's here.
I think your coordinates were right the first time. I think P was the vertical axis.
Oh, yeah,
before you
yeah.
switched them.
Yes. Oh, you're right. Okay. Sorry. Don't know why I switched them again. Yeah, so I'm going to ask you, oh, please put this on the vertical axis, this on the horizontal axis. And in case I don't say anything, then try to put the price on the vertical axis. But if you do the reverse and I didn't say anything, then I will have to accept your answer, don't worry. Are we only ever going to use the upper right quadrant? Depends. If it's economics, it's it's probable because most of economic stuff is positive. But if it's just math, just wait and see. We are going to use everything, every part of the quadrants. Yeah, so I just okay. If you want, I can put some other part of the quadrants. So did I start wrong now? So 6 and 2, yeah, okay. So this is reversed. So 6 and 2. That's 1 point. Then I have 10 and 0. So that's here. Had 1 and 3. Yeah, that's good. And I had 9 and 1. So that's now we have a very nice curve. So that's more than enough to see what's going on. Of course, I don't want something perfect, but I want to understand more or less what's going on. All right, let's use blue. Oops. And this would be, it would continue. I don't know how, but let's stop here. Okay. And now so I'm just going to copy it. So QD equals 10 minus P squared. And I had QS P equals to 3P. So do I have suggestions for points for that one? Supply. Three, 1, 1, 3. So if I have this equals to 1 or 3, 1. So you're saying if I have 1, then I have 3, right? Yeah. So 1, 2, 3, and 1. And then an easy one, 0, 0. Oops. Oh, and I find my intersection point there. All right, so that's what it would look like. Questions about this? All right, it's 10 o'clock, so maybe you can have a break if there are no questions. Oh, we're good. So again, you try different values until you have enough to have a nice curve, at least 3 if it's quadratic, and 2 is good enough if it's linear. So that's if you do that, then I know for sure that you understand how things are going, because we see graphically that we have an equilibrium. And where would have been the negative equilibrium? Well, probably this would have gone there, and we would have -5 over there. So do we care about it? Well, not really. We're dealing about positive values and price. All right, so let's have a 10-minute break, or 10, 12-minute break, and then we can come back. And we're back. So question, what about higher order or higher degree polynomials? So imagine I have, for instance, x4 plus 5/2 x3 minus 5/2 x2 minus 5/2x plus 3/2 equals 0. Is there a way to solve that? Taking factors, how do I do that?
Like we did in Math 202, I think.
Okay, so do you remember? I didn't
I
do.
can hardly remember that.
So I'm going to show you a technique that's technique. I think it's invented by Gauss, which was probably the greatest German mathematician. That works for any rational polynomial. Rational meaning that you can express the coefficient as fractions, and the roots are rational too. So if it wouldn't work for stuff like if you have √2 or pi inside it, then you cannot find a nice solution. But if you can, then yes. How can I do that? Well, consider the following. Yeah. Sorry. It's okay. All right. So consider the following. I have, let's say, ax plus b times cx plus d times ex plus f, right? So if I multiply all these things together, what do I get? Oh yeah, it doesn't give me anything. All right, I get this. Yeah, actually, it's better to divide everything by their. Yeah, first thing I'm going to do is this. So it's still 0 because I can divide everything by stuff here, and 0 divided by it, it's still 0. All right. And if I expand this, I get what? All right. So I get x3 here. Why? x3 is x times xi times x. And here I get, oh, this messy thing here. Yeah. Oh, I'm not happy with my program. Okay, so this term here is the constant term, and this constant term is equal to B df divided by ACE. Yeah. So maybe doing just degree 2 is easier. So yeah, sorry about that. I thought my computer would collaborate better. So imagine I'll do it by hand. Okay, I have ax plus b times cx plus d equals 0. Then what are my two solutions? So two solutions. So x could be equal to, so I see that if I divide by a, then I get, yes, exactly. So I could get minus b divided by a. And I could also get minus c divided by minus d divided by c with that one. So that those are the two roots. All right. And now what Gauss showed is there's an automatic way to find what these are. So if I multiply this, I get. So let's start by dividing by A and C. So I get this, which is still true because 0 is divided by AC is still 0. And then let's multiply this. So I get the following. I get x squared plus b over a plus d over c times x plus then the two other terms here are these equals to 0. Right? This is what the last term is what I get when I multiply b over a and d over c. And what do you see? You see that my last term is a product of b and d at the numerator and a times c at the denominator. So this is rational. And I can try to decompose it. So what I'm looking for is this expression there. And I know that, so I have 1 in front of the x here, and here at the numerator, I can have b times d, and I have to find them. Sorry, my voice is not that good. And here at the denominator, I have a times c. So what is my last, going back to my example here, what do I have here? I have 3 and 2. So I know that 3 is, so if I have degree 4, it means that the numerator is probably the product of 4 numbers that I can factor, and the denominator is probably the product of the 4 numbers that I can factor. So let's try and look at all the candidate solution. So the trick is to not look at two things twice. So yeah, so this is the idea. So back in the example. So the constant term here is made of products which we can factor. So what could be the factors of 3? So factors for
1 and 3.
yeah. One, 3. I would have also -1 and -3, right? But I'm going, yeah, I'm going to write positive factor. And then positive factors for the denominator. I would have 1 and 2. So then what kind of fraction could be made? So what I'm looking for is something like B over A or D over C. So possible. Yeah, so roots. So I could have, so all the possible combinations of them. So you see that essentially that's the Cartesian product. I have two members here, and I can have all the combinations, but I could have also all the combinations with the negative numbers as well. So I could have 1 over 1, 1 over 2, and then
Sir,
3
could you
over 1.
explain how did you get the positive factor for the numerator?
Positive factor for the numerator? Oh, it's
Yeah.
3. I have 3.
I'm a
So
bit
3 is,
confused.
yeah, so the possible factors are 1, 3, -1, -3.
Okay, okay.
And then 3 over 2. And then all the possible negative factors as well. So -1, -1/2, -3, 1, -3, 2. And of course, if I get something like so if I had 2 over 2, for instance, then I wouldn't consider that one because 1 over 1 is the same thing, right? So I could just not consider it. So here are all the possible values that could have gone into these factors there that made this beast of a polynomial. All right. So here I'm kind of nice with you because I gave you 3 and 2. If I gave you 12 and 25, then it's just a complete mess. You have tons of different possibilities. So it's not super convenient to do. So it's possible that if I ask you to solve this at the exam, you might get something simple here. So I'm telling you, so you don't get discouraged. All right. So now let's try stuff.
Sir, I have a question.
Yeah.
For the positive factors for the numerator, why didn't you include 5?
Because 5 is not a factor of 3.
Okay. Thank you.
Yeah, if I could have had something like 15, but then I would have had 10 here. And of course, I would have gotten rid of these things. So 3 divided by 2 is fine.
And what about like square roots?
Well, it doesn't work for that trick. Well, it depends which one, but if it's a square root of 2, then no, it cannot use this. So you would have to use, the formulas by Cardano, and we're not getting there. It's way too complicated.
So for the number of roots we need to get, we only consider the constant part of the whole equation.
Yeah, so that's the nice part of it. You can just not care about any of these numbers there. Just make sure that there's a 1 here, and then you just look at what is the ratio here. And that's it. Then you try all the possible combinations of factors that give you the denominator, all the possible factors that give you the numerator, combine them, and then add all the possible negative values as well. And then all we have is to tediously try one by one to see if it works.
And
All
how
right?
about if we have like a constant term in front of like the x raised to power 4? Let's say we have 2. How would that be? Because it's long back. I've done this part.
Oh yeah, so if you start, if I give you this, 2, and then you have 5, 5, 5, and then 3. Imagine you started with that. Well, the possible solution for x that solve this polynomial equals 0 are exactly the same as
Right.
the possible solution for this. So you just divide by 2 everywhere and you get this.
Perfect. Sorry, I got it now.
No, sorry. It's that's the same thing I was asking myself. So yeah, perfectly good question.
Thank
Okay,
you.
so now we tediously try everything. So trying 1, 1/1. So you just see if it works. So we get 1/1. And then once we compute this, we get 0. Wow, 1 works. Magic. Well, we were lucky. But it doesn't, so yeah, so we get 0 equals 0, so success. So it means that 1/1 is going to be part of our roots. So now what we can do is divide the last, divide 3 by 2 by 1/1, which we just found.
So, and just a quick question: if the polynomial were to be all positive, we would just take positive factors, correct? Or we could also take negative factors, because the
Yeah,
negative
also
and negative
negative.
could be equal to positive. Okay.
Mm.
Okay.
Well, actually, think about it. If you have only positive coefficients and you have x positive, so is it possible that this would equal 0?
Yeah, no,
No, not possible.
not
And
possible.
one other thing I want to make you realize too. Yeah, side note about 1. So could we have known before that 1 would work? Well, if you have 1, then x to the 1 equals 1. So x equals 1. Then it means that we get x to the 1 equals 1, x to the 2 equals 1, x to the 3 equals 1. So what does that mean? It means that this is 1, 1, 1, 1. So then if it works, then it should be the case that here I have 1 plus 5/2. Sorry. Minus 5/2. Minus 5/2 again. Plus 3/2 must be equal to 0, right? Because whatever, so if x equal 1, then this is 1, 1, 1, 1. So the sum of all my coefficient has to be 0. And so is it the case? Well, I just computed it. So yes, so 5/2 minus 5/2. Then this is 2/2. Yeah, 2/2 plus 3/2 minus 5/2 is 0. So yes. So that's a simple trick if you're looking for one as a possible solution. So then what I can do is, so I've found that 1 is a factor. So, okay, so let me get rid of this. Yeah, okay. Yes, I note about 1. So if 1 is a root, then the sum, the coefficients should be 0. All right. So we have found that x equals 1 is a solution. Hence, x minus 1 was a factor. So in that case, what we do is, so we know that inside 3/2, we had a minus 1 there. So now it doesn't give us anything, but so next step is we want to find the other one, so we divide. Divided by minus 1 over 1 and get
Sorry, sir, I lost you. Why did you put minus 1 over 1?
Oh, okay. Because here so this is a product of B over A, D over C, right? So I found that one of these two things is minus 1. Why? Because I tried x equals 1 and it was a solution. So then I know that this product here was made of one of these, B over A or D over C or blah, blah, blah. One of these is minus 1 over 1. So now I can extract it from my my product here. So it doesn't look like I'm doing anything now because it's just 1. But if you found like 3 over 1 or 1 over 2, then this would get even simpler, and you can continue on finding the other roots.
Right, but I didn't get why it's minus.
Oh, because I found that I tried solving it with 1. Okay, I tried x equal 1. Okay, this you understand? What I did is I tried substituting x equals 1.
Right.
And I found that this gives me 0. And this 0 equals 0. So success, it means that x equals 1 is a potential, well, is a solution for this polynomial. So this polynomial is a product of 4 expressions like this, x plus b over a, x plus d over c. So I have 4 of them, and I found that one of them, 1 is a solution. So it means that I need to have 1 minus 1 equals 0. So here I'm going to get that, yeah, x minus 1 is one of these factors, x minus 1 over 1.
Okay, gotcha. Thank you.
All right. So this is complicated. It's a lot to process at once. So if you're confused, So I'll tell you what I do as a student when it's going very fast. So at some point I lose the track of the detail, but I keep what we're doing in the goal of what we're doing in mind. And then I know that, okay, I'm just going to go back on this myself, do all the steps, and be sure that I got that I know how things are working. But if the bad thing to do is just to say, oh, I'm lost, and I'll just check Facebook, for instance. No. Just try to keep the big picture in mind and know that, yeah, the small details, you can get them later. All right. So now we have new constant term. Is -3/2. So what this means is that this is equal to x minus 1 times another polynomial, where the last constant term would be now -3/2. This is what it means. I'm not showing you how to divide it, but it's possible to do it. Yeah, if we have time at the end of the semester, I would doubt it. But if we do, then I'll show you how to extract a factor like this from a polynomial like that. It's not too complicated. Actually, it's something you can try for yourselves. Okay, so now we do the same thing. Yeah, synthetic division. I don't know how. I think maybe I've seen this in my youth, but I forgot how it works. But basically, it's a bit like completing the squared. It's saying like, yeah, I'm just going to put you on the track. So if okay, so side note. So extracting x minus 1 from this. Yeah, I'll do it quickly, and then this is just for people who are interested, right? So I know that here I have x4, which is going to multiply. So this x4 is going to be, so what I want basically is to have x times x3 times, oops, sorry, x minus 1 plus 1, okay? x4 is exactly that, right? Everybody agrees? So then just multiply it. So I get plus x3 here, oops. And then, so that's 2/2 plus, so that's 7/2. So maybe synthetic division is the same, basically. Yeah, so I have x3 here. So I want this to be x2 times x minus 1 plus 1. So I'll have plus this is there. Minus, so 7 minus 2, that's 1. Right, 2 over, it's going to be 2/2, so 1. And x2 is x times x minus 1 plus 1. So probably a synthetic division is exactly that. I'm not inventing anything. plus x. So that's 2/2 minus 5. So that's minus 3/2, right? So I get, and this is, yeah, well, basically here it's minus yeah. So I get, I can put the x minus 1 here. And you see that this is what I was saying here, is that now we have a new constant term here. And now what we're factoring is this new thing there. Yeah, maybe that was good to do, just to show you where we're going. So we found x minus 1, and now we have this new constant term here, minus 3/3, minus 3/2. So are you mesmerized, or did you follow a bit?
Yeah.
Right. So I think if you do it with it's, I don't know, I don't like to call these, I think this is, it neatly shows what, so that's something you're going to see is almost everything I do is multiply by by x over divided by x, or add 0 in the form of -1 + 1, for instance. So doing it this way, you really see where things comes from, basically. Okay, so we have this new constant term. Possible. So here nothing changes. So possible factors for the numerator are still 1 and 3 for positive factors, and 1 and 2 for the denominator. So the possible roots are still the same. Yes?
Since we found 1 as a value, since we found that giving x a value of 1 gives the formula a 0, we found out 1's a root. So wouldn't that mean that we could take -1
Oh, we could
of
take
the possible roots?
All right. So here it's subtle. So that's exactly what I was going to go to. So thank you. That's you're anticipating what I'm going to say. So here's the point. If I'm continuing with this polynomial here, I don't know anything about it. I know that my big polynomial was x minus 1 times something. Now I have this new polynomial. Maybe 1 is also a factor of this new polynomial there. But if I suggest you don't do this thing, you could do this thing and continue on. But as I was saying, you know that you're going to get x3 here because we started with x4. And you know that you're going to end up with -3/2 because we just divide by -1. So we know that we end up with this. And as I told you, we don't really care about the middle terms here. So this takes time. And since life is short, so yeah, it's best to not do this thing. I just wanted to show you how you could do it. But then as if we don't do this, then it means that we continue with this big polynomial here. And you're perfectly right. In that case, if we try again with 1, we're going to get success again. But it's all it means is, oh, we have found what we just found before. So since we're just divided by -1 and getting this, then you're absolutely right. Now we're just going to exclude 1.
So correct me if I'm wrong. It's better if we just do the trial and errors with the first polynomial and get it over with, right? Rather
Yes,
than doing
exactly.
additional steps. And, okay.
Okay, so let's continue.
And then I guess my question was more, since we found x minus 1 as a factor, we can't take out -1 over 1.
Well, no, because we haven't tried it. Maybe it works too. Who knows?
Right. Okay, so we can't eliminate it yet based
No.
on the opposite side being the root.
Yeah. Oh, I don't know. Maybe there's some mathematical reason we could. I'm not too sure, actually. Yeah, because it's if I have something like x plus 1, x minus 1, I'm going to find x squared minus 1 as a solution. And then I have 2 roots, x plus 1, and well, two factors, and x minus 1. So the fact that I found 1 doesn't include that I could get a -1 there, or vice versa. So yeah, you just exclude the one that we already found. Okay, so now let's continue our trial and error. So trying 1/2. So I'm looking for, and I'm going to, so this is, I'm not going to use this one. I'm going to continue with my initial one. So 1/2, 1/2, 1/2, 1/2. Thank God for computers. Yes. 0. Woo! How lucky we are. So success again. Yeah, so let me put this here. So 1/2 is so x minus 1/2 was a factor. So we divide minus 3 by minus 1/2 and get as new constant term 1 over, oops, sorry, 1 over, oh, sorry, 3 over 1. So now it gets easier. So possible factors, positive factors for the numerator, I get 1 and 3, and possible positive factor for the denominator, I get just 1. So then possible roots, I get 1 over 1, 3 over 1, and then minus 1 over 1, minus 3 over 1. But I already know that 1 over 1 is one of them. So I, again, excluding 1 over 1, which we already have. All right, so trying 3/1. Oh, 120. So no. So that's not one of them. So trying. -1/1. Zero. Yeah, so thank God we didn't exclude it, because it was a good one. So we know that x plus 1 as factor. All right, so yeah, what do we do now? We have found x minus 1/2. Oh yeah, so now I know exactly what I should get as the last one. So last factor should be so I was 3. Wait a second, I tried 3. Oh yeah, -3. Sorry, yeah, should be -3/1. That's the last one that we haven't tried. So -3/1. Zero success. So we have found our answer. So that's it looks like magic, but you have to work for your meal. And that was a easy one. Imagine if you have like let's say 4 possible factors there, and then 4 possible factors there. So you get 16 plus you get all the negative numbers. So you get 32 things to try. So that's a whole lot of fun. So if the exam is 3 hours, then I can just give you 3 hours to compute everything by hand. Yeah. So what should you do about this method? Well, it might come in handy at one point in an exam if you have some polynomial that's a higher order. Yeah, but what was said by Mr. Jacobi is exactly right. Thank God we have computers. So the solution is this. So get yeah, what did we find? Oh yeah. So x plus 1 times x minus 1 times, what did we have here? X minus 1/2 times here it's x minus 3. So if I compute this, what should I get?
Sorry, why is it not +3?
It's Oh, because that's oh yeah, you're right. Yeah, I think. Yeah. So yeah, even I can get confused once. So I don't know. Maybe my computer is going to factor it for me. Maybe not. Let's see. Oh yeah, and there's a 1/2 in front. So x minus 1. Yeah, so that's if I put the 1/2 here. So I get x minus 1/2 and x plus 3, you were right. Okay, so we're good. So the roots.
I think it's x minus 3. I don't know. Can I share my screen?
Yeah, sure.
Okay.
I'm going to. It's Charming Tang, right?
Yeah.
Okay, share your screen for us.
God. Is it a virtual background or I'm not sure.
Yeah, the thing, yeah, but yeah, let's not do that because yeah, we just checked and -3/1. Yeah, no, the thing is I shouldn't have written this last root. Should be -3/1. So last factor. Oh yeah, now you're maybe not seeing anything. Is my screen still shared?
Yes.
Yeah.
Okay, good. So yeah, I shouldn't. The thing I wrote is last root should be -3/1. So last factor is x plus 3. Yeah. So we are done. Yeah, because yeah, that's because I've tried -3/1 and it works. So it means that if I substitute x equals -3/1, I find that -3/1 plus 3 equals 0. So that's what we're after, right? So that's why it's the solution.
Sir, I have a question.
Yeah.
So if you go up like to the very top where we started doing all the possible roots, you said 1 by 1, 1 by 2, all of those.
Yeah.
Not sure where it is. Yeah, the constant
here.
is 3 by 2,
Yeah.
right? Is it not possible we just put all of them in the equation and check if 0 equal to 0?
It's exactly what we're doing. Yeah.
Okay, because wouldn't it be quicker if we just put all the numbers 1 by 1 in the equation, then to go through them like this?
Yeah, it's possible. So here it looked like I was wasting time, but so here, for instance, what was nice is since I found where is it? I found 1/2. So then I can divide by -3/2 by -1/2. And then a new constant term is here. So I know that I can forget about like -1/2, -3/2, or 3/2. I can all not care about them because the 2 is gone. So here it's sort of removes almost half the choices I have to try. But you're right, you could try all of them.
And other thing, let's say for this equation, 1-on-1 worked. Let's say it was 1 by 2 was the first number, and if it didn't work, so we'll go to the next root to check. So
yeah. So you check 1/1, then 1/2, then 3/1, then 3/2. By the way, this is something you may do is if you want to simplify your constant term, then starting with 1/1 may not be so useful, because as you've seen, I divide by -1 and I get something as complicated. So I should have tried with 3/2, 3/1, 1/2, these things. So then it simplifies faster. If you see what I mean. Yeah.
Perfect.
All right. So I don't know if I have a quiz on that, but yeah, it's a bit complicated to it takes time. That's the thing. It's a procedural. So what I like about this is showing you where it comes from. So showing you that we can reflect about how these polynomials are made and come up with some and how to divide by x-1 to this is nice. So it may be helpful for you to factorize stuff. All right. So did I have another example? Oh yeah, and one thing that I can do with this is plot it. So let me go on Google. Yeah, so maybe I can share my screen actually. So sharing my screen. Okay, so if you're on Google or anything, oh, I don't know what happened there. Okay, and then you just write it down. It's going to give you the nice formula. So the formula was, I'm trying to find out. It's, where is it? Oh yeah, okay, so y equals, oh yeah, I think I tried it once. Yeah, is it? Yeah, 2x4 plus 5 x2. Yeah, I think it's this. Yeah, and it gives you the solution exactly. So that's neat. So you can see all the solutions we found. We found +1, 1/2, -1, and -3. So let me print this. All right, so let me make it smaller a bit. Okay. How long have we got now? 20 minutes. So I can ask one thing. So question. Why is it going to infinity for small and large values? Any idea? So what I'm saying is, if it looks like if I'm going to a large value here, this is going to infinity. And if I'm going to very small values, it's, yeah, you don't see it, but it's going to plus infinity too. Plus infinity.
Because the positive terms apply to the constant and then x to an odd power and x to an even power. And so because it's applied to both positive power, even and odd powers, you have a positive term before those exponents. That's why it's going to positive infinity in both directions.
Yeah, I think, let me tell you what I was going to say, and you can tell me whether it's the same thing. So what really matters is, so the question is, when x becomes very big positively or very big negatively, what matters in this polynomial? So the constant term at some point doesn't matter. This one either, this one either, this one either. What's going to dominate is the bigger term here, x to the fourth. Because if you have like x equals 1,000, then this is 1,000 with to the fourth. So that's huge number, and it just crushes all the other ones. So then if this is positive, you're going to get something that looks like this. And if there's a negative sign in front of it, then you're going to get something that looks like this here. So yeah, it's, and if you look at in this form, how can you see it? Well, you always have 1 and 1 and 1 and 1 in front of it. So you have positive coefficient and you have a positive coefficient. So you know that you're going to get x4 in front, and it's going to have a positive value. So the quick answer is because the higher order term. Oh, and I think, yeah, I think what you wanted to say is something about the fact that it's also an even exponent. Was it?
Yeah. The reason I brought that up is because if the highest power was an odd value, yes, you would be going to positive infinity in positive x space, but in negative x space, you will be going to negative infinity because it's an odd power, and a negative value to an odd power is still negative.
Yeah, exactly. So you're exactly right. So higher power term is even as exponent and positive coefficient. If negative coefficient plus, the function would be going to minus infinity for large positive and negative x if odd coefficient exponent, highest exponent, then plus infinity on one side, minus infinity on the other. Yeah, maybe there would have been a simpler way to than just writing it all in words, but yeah, haven't thought of it beforehand. All right, so what I can tell you is, so exercise for at home. Find the factors for or find the roots better for x3 plus 4x2 plus 5x plus 2 equals 0. Of course, you can just go in Google and draw it, and you have all the answers right away. That's the fun of teaching in modern times. But that's why you have to show your steps at the exam. So if you want your points. All right, so there's a multi-market equilibrium. Do I start this or not? What do we say? Or do you have questions about everything we just did? It's procedural, it's tedious, but it gives you the right answer if the right answer is rational. And by the way, I'm not going to fool you into giving you root 2 or whatever. I'm going to, this has nice solutions. Oh, yes, Mr. Sheikh-Miri.
Sorry, it has nothing to do.
Oh, sorry, I called you Mr.
No, it's not a problem. It's not in regards to this specifically, but I just want to know, would you say that we can complete in full the assignment as of today? Basically, have we covered everything that's in the assignment?
Yeah, there's just a multi-market thing that I was going to start. Yeah, I can start it in 10 minutes. But it's just an extension of what we already know. So you could more or less guess how to do it. But I'll just say briefly what's going on. Okay, so last topic, multi-market equilibrium. So what's going on there? It's, of course, not, what we've seen so far is a single market, but that's not what you would call general equilibrium. Because everything that happens on one market influences what happens on many other markets. So we're going to see a multi-market, I would say multi-market partial equilibrium. Why? Because it's less partial. So I'm guessing that the book is going to go into much more detail in many topics. Some of them I had prepared, and then I thought, oh, maybe it's a bit too mathy for you. It's better to stick with things that really touches economics. But of course, yeah, you can read all the book. It's very well done. The examples will look like what I'm doing here, but maybe a bit different too. Okay, so general equilibrium all markets plus budget constraint. So that's what we're doing here. So this is just partial equilibrium with many markets. So example, if I have two markets, so market demands would be, so I think I could go with the numeric example right away. It's yeah, it's good enough. All right, so market demands. So I would have QD1 equals 4 minus 3P1 plus P2. And I would have QD2 equals 12 plus 2P1 minus 2P2. So why do I think it's valuable to model two markets at once? Well, if I think that the product in the price in one market will influence the demand for the other product, then it makes sense to have a big system with two markets inside it. All right. So questions. Well, okay, I'm just going to say where I is demand for market. Yeah, quantity demanded. Yeah, good demand for market I equals 1, 2. Is product 1 a substitute or complement of product 2? What do you think?
It'll be a substitute.
Why?
Actually, no. Sorry. It'll be a complement. I misread, because as the price of the second item. No, I was right the first time. I'm confusing myself. It is a substitute because as the price of good 2 increases, the quantity demanded of good 1 also increases.
Yes. So good 1 is a substitute for good 2. Yeah, for good 2. Since price P2 increasing leads to an increase in cube D1. And I don't know what you learned, but I'm teaching micro right now, the 201. And they say that, oh, if this is the case, then it means that both are substitute of the other. or both are complement or of the other. But this is not the case. I could have a situation in which I have, for instance, -2 here. So you could see that if the price of this item increases, then this quantity demanded increases. So product 1 would be a substitute to product 2, but product 2 would be a complement of product 1. It looks very weird, and it doesn't happen often. Normally, you would think that the two are, so I'm going to stick with what I had. So usually if one is complement of the other, then the other is complement of the first one, but in reality, we cannot say that for sure. So just to give you an example, good 2, good 1 is, I don't know, tea, and good 2 is coffee. So if the price of tea, if the price of coffee increases, then people think, oh yeah, no, I don't care all that much about buying coffee if it's too expensive, so I'll go buy tea instead. So that's why if P2 increases, then the demand for tea will increase. All right. And then question. So what is the status of good 2 with respect to good 1? I'm going to answer for you. Good 2 is a substitute of good 1. Since P1 increasing leads to an increase in QD2. So you can see it here. By the way, now, what are goods 1 and 2? Ordinary or Giffen? Have somebody heard that before?
The ordinary.
Yes. Yeah, ordinary means when the price increases, the quantity demanded decreases. So when the price increases, the quantity demanded decreases. So Giffen good are, yeah. Giffen is for Robert. Or I don't know how you write it, Robert, maybe. I think he was Scottish or Irish. He was an economist. And yeah, he said, yeah, it's possible to have goods for which when the price increases, people want to buy more of it. But it looks completely outlandish to think that this may exist. But recently, I think some 10 years ago, some economists found a Giffen good. It was rice. And what they found is when they increased the price of rice, I think it was in some Asian country, maybe Vietnam or something, then the quantity that people of rice people consume actually went up. It looks very strange, but what was the phenomenon? Since rice is such a big part of their budget, then if the rice was cheap, they were able to consume some small quantity of rice and some other stuff like meat, like they would be richer. But then if you increase the price of rice, then they didn't have enough money to buy better stuff to go along with their rice. So instead they just stick with rice, and to make up for less calories, they would just buy more of it. So it's very strange phenomenon, but it exists. But yeah, so it's mostly theoretical. We almost never observe this. It's for goods that are super inferior, that goods that as soon as you get more money, then you don't buy it, you buy something else. Yeah, so most goods are ordinary goods. And why? Because, say for instance, P1 increasing to QD1 yes, exactly. There's a super big income effect going on. It has to be a good that is a big part of people's budget. So if the good becomes more expensive, people get super poorer and they cannot buy other things, and they have to make up for it by. So I had one given good in my life. So my colleague in Rennes, he had a very old car. And he was thinking, oh yeah, I should change it. I should buy. I'm saving to buy a new car, but then it kept breaking. So he didn't have enough money to buy a new car. So what he had to do was keep repairing his old car. So he was just spending so much money on this crappy car and never having enough to switch to some better good. So for him, his car was a given good. All right. So we're out of time, and yeah. So next time we just continue this. If you want, I can give you the example of so supplies quickly if you want to do it at home. So QS1 equals P1 and QS2 equals 2 P2. And then you can more or less do it. And you can more or less do all of the, if you can know how to, and then of course solve for P1 star P2 star. Oh yeah, and okay, give me 2 seconds. Oh yeah, no, yeah, it's true. I'm going to give you 15 minutes because then the lab is starting. So to start the lab, go on the Moodle page and click on the link I've put there. So it starts in 15 minutes. So after 3 hours of math, you can go ahead and continue for another hour of math. So yeah, that's the way things are. I'm sorry about this. It would be better for you to learn if it was spread out, but that's the way it is. Yeah, the labs are live, or they're on Zoom. But yeah, they're being recorded, and once I figure out how Moodle works, we should be able to post them. Or you don't have to attend them if the exercises are very easy for you, but it's of course highly recommended. All right, so I hope you have a nice week, and I see you next Friday.
Thank you. Have a nice weekend.
Have a nice weekend.